So we're going to start looking at Unit 6 right now. We've got random variables in Unit 6. So there's the idea of expected value and probability distributions. This would be the things where we say we have specific outcomes that are possible in a certain game or in a certain event, probability event. So my results are 1, 2, or 3. And the probability of these different events is 0.5, 0.25, and 0.25. So from this probability distribution, and remember this has to add up to 1.00, we can find an expected value, which is going to be you multiply those two and add that product to the product of those two plus the product of those two, and that's going to be your expected value. So this entire thing is the probability distribution. The expected value can be found. There's a way of also finding the standard deviation that we would expect from a random variable, and we don't calculate that by hand. Instead, what we do, remember on your calculator, that would be our one variable stats. And we use a frequency list. We'd put in our 1, 2, and 3 as the outcomes, 0.5, 0.25, 0.25 as our probabilities for each outcome, and then we can get our standard deviation, all that fun stuff. Combining random variables. This is if I have a random variable x plus random variable y. Well, the mean of x plus y is going to be the mean of x plus the mean of y. And I should also add that the mean of a random variable is the same as the expected value of that random variable. And the standard deviation of x plus y is going to be adding the variances. Okay, so that's going to be the square root of, okay, that's what I was trying to say. Sorry. Standard deviation, the variance of random variable x plus the variance of random variable y. Okay, just trying to jog your memory, not trying to reteach this. Bernoulli trials, this is where it comes into play. This is really kind of our Unit 7, but no, this was Unit 6. I'm losing track. Yeah, it was. So Bernoulli trials are binary, they're independent, and they have the same probability. So we're looking at repeated events that have two outcomes. Either we fail or we succeed. With every single time this event occurs, it has the same probability of success. And that each trial is going to be independent, so we don't need to worry about changing probabilities. All right, we have BINS as an acronym. That's binary, independent, and same probability. The N is for in set number of trials. So binomial would be questions like, how many successes would you expect out of 10 trials? Or what's the probability of getting at a minimum 8 successes out of 10? Those kinds of questions. This is almost guaranteed to be on your AP test. So binomial is going to be an important one to know about. Geometric series is going to say, what is the probability that the first success is the third time? Or kind of a hidden way of doing this is, what's the probability that someone takes at least 4 times, tries 4 times before they succeed? So that's the probability that they don't succeed the first, second, third, or fourth try. Anything after that is fine. But if in your head you can realize we're talking about something about the first success, that's what the F stands for with your geometric probability. So the binomial and geometric right here, number of trials until first success. Okay, that's a very short intro to something it can be kind of complicated. So let's look at a few examples here. Maybe I'll just talk through this one. So because this is a cumulative probability distribution, what we're saying is that it's the probability that a random variable is less than whatever this value is. So this is number of pencils brought to school by children in 2nd grade class. So the probability that 7 or fewer pencils are brought is 0.75. But the probability that exactly 7 are brought is going to be this value minus this one, which is 0.125. So if I ask what's the probability of exactly getting 7 pencils, then it's going to be 1/8, 0.125. All right, is this all making sense? Coming back to you to some degree? Okay. So as this goes, the probability for each outcome is 0.125. So I'm just going to draw this arrow coming all the way down, except for here, the probability is 0. Honestly, that shouldn't be a 0 right here. That should be another 1. But we didn't add anything from here to here. So the probability of this outcome is 0, meaning the probability of 10 pencils is 0. So 0.125 for everything. So our distribution looks like this. Going all the way from 2 to 9, we have our 0.125 probability. So the question is, what is this going to look like? Your friend claims that the distribution of this random variable t is skewed to the right. No, it's not. It's uniform. So it's not skewed at all. It's a uniform with either a mean equal to 5 pencils or a mean greater than 5 pencils. You can plug in a probability distribution and figure out what the mean is. You can also realize that the mean is going to be, if you have 8 values and they all are equally likely, it's just the average of all these values. So basically I can just get the average out. This only works because it's a uniform distribution. If we had different probabilities of different outcomes, we would need to plug this into the calculator and do our frequency list. But in this point, at this case, if I add all this up, then I'm going to get 5.5 as my answer for the mean. So the mean is going to be greater than 5 pencils. Okay. I don't know if that seemed easy enough for you. All right. I might give you guys a little bit of time. I'm not going to spend too long on any one problem, but I will bring up a poll, and I'll just let you guys kind of work through this one first before I run through it. In this problem, what we want to remember is that when we are transforming our random variables, the mean is affected by addition, subtraction, and multiplying, but the standard deviation is only affected by multiplying. Addition doesn't change your standard deviation. So what I can do is, for the mean of S, it's going to be 7 plus 2 times the mean of R. So that's going to be 7 plus 2 times 8, which is 23. And there we go. I'll just cross these out. Oops, I shouldn't have crossed that last one out. All right, the other thing is that the standard deviation of S is going to be only 2 times the standard deviation of R, because we don't do the addition here. Okay, it's hard for me to think today. It's very much a Friday. So the standard deviation is 21. So that means 42 is the standard deviation. So the answer is right there. All right.
I remembered that you didn't do the addition, but why is that?
Okay, well, let's go back to that. Why don't you do the addition here? We can think of addition as, because a random variable has a distribution. Let's say it's a normal one. When you're adding and subtracting, all you're doing is shifting this left or right, but you're not actually changing the shape of the distribution. When you multiply, you're changing the shape in some way. Actually, it wouldn't look like that. It might look like this. So if I multiply, it might look like this, or it might look like this. Actually, I probably should have done it the other way. But whatever the case, when you're multiplying, you are actually changing so that the height of it would go up and down, but that doesn't matter for our purposes. So when we're multiplying and we're changing the spread, then that changes this distance right here, which is our standard deviation. Maybe here's the standard deviation for the first one that we had, the original. Then we have a smaller standard deviation. Then we have a much bigger standard deviation for that widest one. So multiplying affects your standard deviation, but the addition is just going to shift it left or right, but the shape of the distribution won't change. Okay. Okay, another one right here. This is definitely getting into more of the mathy side of this. See if you can figure it out. In this problem, we are looking at a binomial situation. We're assuming that each hit, each time up to bat is independent, that he either gets a hit or doesn't, and that it's the same probability each time. He's really truly a 28%, a 280 lifetime hitter. So he's going to get 600 at bats, and we want to find out the probability of 200 or more hits. So basically, with binomial probability, we can do what's called a binomial PDF, which says what's the probability of getting exactly a certain number of hits. Or we could have a binomial CDF, which says what's the probability of getting anywhere from 0 to X number of successes. So that's what we want to know. We want to find what's the probability. We can't get the probability of 200 or more directly, but we can get the probability of anywhere from 0 to 199. And then if it's 0 to 199, and then that we can take the complement of that, then we're looking at the probability of getting 200 hits. So I'm going to do 1 minus the binomial CDF probability of, and this is where if you go into your binomial CDF interface on the calculator, you're going to see your options. It's going to be number of trials. He's going up to about 600 times. He has a probability of getting a hit of 0.28. And we want to get up to 199 successes, because anything from 0 to 199 isn't what we're looking for. So if I do the complement of that, it's going to be 1 minus that, and that will give me my answer, which is 0.002. There's only a 0.2% probability that this batter is going to be able to get 200 or more hits in a season with 600 at-bats. Okay. Now, I didn't get very many responses on that. So are there questions that come up from this?
Wait, one more time, what's the difference between binomial PDF and CDF?
PDF says what's the probability of getting exactly a certain number of successes. CDF says what's the probability of getting a range of successes starting at 0 up to a certain value.
Gotcha.
And the C stands for cumulative density function. P is probability density function. I mean, it actually might be slightly different from what I just said, but essentially the thing to remember is C stands for cumulative. All right. So was there anything else I was going to say to that? Oh, yeah. Remember that a binomial distribution is going to look something like a normal one if you have enough data, that is. So if it gets big enough with enough events, it's going to look a little bit normal. So what we're saying is this. The mean of this is always going to be, the mean of a binomial distribution is, I'll just put x for this random variable x, is going to be n times p. So there are 600 trials with a 0.28 probability of success. So this isn't what they're asking for in the problem, but we can still figure it out. 600 times 0.28 is 168 hits. So this is going to average to 168. And 200 is going to be up here somewhere. All right, so there's only a 0.2 probability, 0.02 that, or yeah, 0.2% probability that 200 is the result, 200 or higher. Okay, so it's very similar to a normal distribution, but we do have a different function for that. All right, give this one a go. For For this problem, you will want to refer to your AP formula sheet because you're probably not going to remember exactly what to do for this. You can figure out that we're looking for an expected number of candies, and we basically have a binomial situation because we have a set number of trials. Each one of these candy is a trial. So there's 2 independent random samples, each is size 20. So when you combine them, then it becomes a sample, total sample of 40. How many orange candies would you expect in the combined sample? So this is because we're dealing with a certain number of trials and we're looking for the number of successes, we are going to be looking at binomial. And I want to make sure I'm doing this right. There it is. So right in the middle, you can see we have our formula for the mean. This is just going to be for one random variable, and then the standard deviation just for one random variable. So make sure you're paying attention and you can see where that's located on your formula sheet. See what that is, Eli? Okay. So that's what we're looking at. Knowing that, I'm going to find the mean of dynamite mints, the mean of holiday mints. I'm going to get the standard deviation of dynamite mints and the standard deviation of holiday mints. The mean is going to be n times p. The standard deviation is the square root of n times p times 1 minus p. And I won't write, it's the same equation for both. So n times p here is going to be, there are 20 mints times the probability of orange is 0.12 for dynamite. This is going to be 20 holiday mints times 0.6. And then whenever I plug in for this, it's going to be 20 times 0.12 times 0.88. And we'll get our answer for this, which is 1.453. And this will be 2.4. This is going to be 12 for our expected, for our mean, which is the expected value. And then when we do 20 times 0.6 times 0.4, we will get 2.191. So now what we're doing is we're taking this, the expected value and the standard deviation of each, and we're going to combine this. So the total number of successes taken whenever we have, so just to clarify what this means, out of 20 dynamite mints, we'd expect 2.4 to be orange. Out of 20 holiday mints, we'd expect 12 to be orange. Out of dynamite and holiday mints put together, that we would expect 2.4 plus 12, or 14.4. Because that's just the mean of dynamite plus the mean of holiday mints. But for the standard deviation, this is what we mentioned a second ago, dynamite plus holiday mints would be the combined variance. So that's going to be the square root of standard deviation of dynamite squared plus the standard deviation of holiday mints squared. So in this case, it'd be 1 square root of 1.453 squared plus 2.191 squared, which gives us 2.629. And your answer is D. So this is probably telling you guys stuff you need to maybe go back and look over again. Or maybe you see this and you're like, okay, now it's coming back to me. All right. This is one that a lot of people missed, and I wanted to look at this one specifically. The random variable x has a geometric distribution with a probability of 0.37. Approximately how far do the values typically vary on average from the mean? They're asking with this, how far do the values of w typically vary? That's another way of saying, what's the standard deviation of x? Well, it should have, okay, I have x and w, so let's call it w. All right, so the standard deviation of w, this is a geometric distribution. It even says geometric distribution. So we're looking for the standard deviation of a geometric, which is this. The square root of 1 minus p over p. And that's found, again, straight from the front. I don't have that memorized. I looked it up as I was writing it down. It's right here. Because it's geometric for this row. I'll look at the standard deviation. And now it's pretty straightforward. It's just going to be the square root of 0.63 over 0.37. And when I do that, I think it's 2.15, but we'll double check. Yeah, 2.15 is the answer. Now, geometric is not as common to see on the AP test, but it's not like you're never going to see anything related to it. But binomial, you will definitely see. And I can almost guarantee you're going to see it as part of an FRQ. So geometric is less likely to be something that you'll come across. But again, know where to find the information about it. Are there questions? Okay, let's see. I think, okay, we just have this. This is another one that a lot of people were missing, so I kind of picked the ones that had the lowest correct responses for them. So in this case, we've got a die that has 8 faces, 3 red, 4 yellow, 1 blue. When you toss this enough, you toss it until the blue lands face up, and the number of tosses before blue lands face up is counted. What's the probability that the player will toss the die at least 4 times before blue lands face up? So it doesn't ever say the word first, but we're trying to find the first success, and it's weird that success in this scenario is getting blue, which means you lose. So a success is actually losing. All right, so the probability of success is 1 in 8, which becomes 0.125. All right, because we can see there's 1 out of 8 faces. So we can find the probability that we succeed on the first try, which is going to be 0.125. I'm not going to run through this in great detail, except to say we want to find out, okay, we don't want to succeed on the first, second, third, or fourth try. But if we succeed, and that is failing in this case, if we succeed by getting the blue on the 5th or later, what's the probability of that being the case? So what I want to do, the thing that makes the most sense to me is looking at a geometric CDF probability. This is a cumulative probability of getting a success on the first, second, third, fourth, fifth, whatever trial up to a certain number. And we just want to put in the probability, which is 0.37. Or no, I was going back to the previous problem. 0.125. I don't want to put the parentheses. And the number of successes. I want to make sure I'm not leaving anything out. So our probability and the number of successes up to 4. So this calculation says, what is the probability that we're going to succeed on the first, second, third, or fourth try? Any one of them, doesn't matter which. And we'll get that number. But we don't want to get a success on the first through the fourth. We want to get the probability of not succeeding on any one of those 4. Does that make sense? So at this point, if I take the complement of it, that'll give me my answer. So it's going to be okay. My answer is B when I do that, 0.586. Okay. Now remember your geometric CDF and PDF. PDF would be what's the probability of getting our first success exactly on the second, third, whatever trial we're interested in. Normally with geometric, it's a CDF function, but it could be a special case. The binomial and geometric PDF and CDF functions are under your distributions menu. So you can look for that. Unit 7. This is kind of an oddball unit. It was really the beginning of everything dealing with inference, because what we're talking about is sampling distributions. And the idea behind it is that when we are looking at inference, we're not looking at one specific variable value from a specific person in the population. We're getting a sample statistic, a mean, a proportion that comes from a sample that we drew from the population. So we're not going to be comparing this sample statistic, the sample mean, to the population. We're going to compare it to a sampling distribution. If we took an infinite number of samples of size n from the population, what are the likely values? And the sampling distribution is a normal distribution itself. And the center of that distribution is an unbiased estimator of the true population mean or proportion, depending on the problem. The spread is determined by our formulas. In fact, it's determined by the formulas that we find on this back side of the front page of our formula sheet. So the spread is going to be the second column right here, I believe so. Yeah. And so you can see the formulas. Now the standard deviation of a sampling distribution is the same as the standard error. There we go, right here. Except in the standard error, we have sample statistics being used in place of population parameters. All right, sorry, let me go ahead and fill that in. So the sampling distribution for this is going to be the standard deviation of the sampling distribution for sample means is going to be this divided by the square root of n. And then for the standard deviation for a sampling distribution of sample proportions, it's going to be the square root of p times 1 minus p all over n. And we are familiar with these. And essentially what we're doing is, if our population looks like this, a sampling distribution of size, whatever, let's go with 50, might look like this. And then size 100 would look more like that. And then eventually you get to, something that's really small. Maybe this is n equals 250. So what we're saying is that with the big sample size, the probability that you get a sample result that's far away from the population mean is less and less likely. Okay, just a bunch of review concepts right there. This is actually going back to, oh no, this is a good question. Actually, I'm going to leave this one. I'm going to let you guys look at this one. This question might be, you might see the answer and decide this is a trick question. And one thing that we need to hone in on here is that this is a continuous random variable. This is not discrete. These don't have specific values. It can take on any value on the real, that's a real number. So in that sense, the probability, and this is where it turns into almost a trick question, the probability of any specific outcome, which in this case, 10 would probably live right about here since the mean is 12. The probability of this specific value being a result is always 0. So it looks like this is a calculation question, but really it's a conceptual one. No calculations required on this. Now, if this was a discrete random variable and they're asking for the probability of getting this result or more extreme or something like that, then or getting exactly X number of successes, something like that, then at that point we could calculate the binomial PDF. But I want to clarify, Bernoulli trials are discrete because we're counting the number of successes. You either have 1, 2, 3, or 0, any number of successes, but this is now a continuous random variable. Probably enough said on that. All right. I feel like you guys could be able to handle this one. This one is a little bit of a trick question. Now, it starts off pretty straightforward. We are going to be using z-scores to calculate what the missing x value is. Because we know that we have the mean already, so I'm going to have 0.8 millimeters is the standard deviation. X minus 20 is the 20 is the mean. The z-score, because this is the top 20%, I want to find the z-score for the 80th percentile measured from the left. And so I'm going to do a point.
Why would it be the left?
Well, what I mean is the left is the top 20% is up here, right?
Yeah, so that's how it would be the right.
Yeah, and you have a calculator that can do a right tail. I'm talking about for these calculators, it only has left tail. So we have to look at the 0.8 that's below that value instead of the 0.2 that's above. But if you have a newer calculator that can do a right tail, that's totally fine. You'll get the same number either way, which is 0.8416. So that is the z-score that corresponds with the 80th percentile. So 0.8416. There it is. And when you solve this, you're going to get 20.673. Okay. And that is the value that corresponds with the 80th percentile. Now, the question, this is where it turns into a trick question. Which is the least thickness of a tire? So anything below 20.673 is not in the top 20%. So this is not in the top 20%. That's not in the top 20%. But of the remaining ones, which is the least thickness? Well, that one is. And this one just probably would never even happen, right? So 20.8 is the best answer here. All right. Give this one a go. The answer that most people were able to come up with who answered this was D, and that is correct. The main thing behind this is that the number of trials doesn't really matter as long as it's a pretty big amount. What matters to determine the shape of your distribution is the sample size, because the standard deviation, this is sample proportions. The standard deviation for this is determined by the square root of p times 1 minus p divided by n. So as your sample size goes up, your standard deviation goes down. So 125 is higher than 100, and therefore the simulation 1 is going to have less variability. And that's what we're getting at here. But the centers will not really change. They shouldn't change. Okay. I'll just talk about this one. Same idea. So the bigger the sample size, the smaller the standard deviation is going to be. But also the p-value, not the, no, p-value isn't right, but the proportion, the sample, the proportion that we're looking at can have an effect on that as well. It turns out the closer you are to 5, the bigger the value on top is. So if we just look at this again, the standard deviation is going to be square root of p times 1 minus p divided by n. And so if we are, the way that we can get the standard deviation to be, let me see what we're looking for. We want the smallest standard deviation. So anything in the numerator, doesn't matter that's under a radical, anything in the numerator is directly proportional, meaning as your P times 1 minus P, as that goes up, your standard deviation is going to go up. And then anything in the denominator is inversely related. So as your sample size goes up, your standard deviation goes down. So we already know we want a big sample size. So I'm going to cross those three out. But we also want to, if we're trying to make this smaller, let me flip the causal arrows here. As my P times 1 minus P goes down, this also goes down. And you can experimentally figure out which one makes it the biggest, but what we learned is that 0.5 gives us the biggest value in the numerator. So that's going to be 0.25. Anything closer to the extremes, 1 or 0, is going to be a smaller value up top. So we want to have the smallest value in the numerator and the biggest value in the denominator. So in this case, our best answer is this. Okay. Let's see how much more. Okay, we don't have much more. We can do this. I'll let you guys look at this. Lots of conceptual questions on this. Let's see if you can handle this. The way that I first approach this is trying to figure out what is the mean of our sampling distribution for means going to be. And I can find that, well, sorry, it's for proportions. Find that right here. It's one sample. So the population mean is going to, or the mean of this distribution is going to be the same as the population. And then here's the formula we use. So we can actually just do that real quick. The mean of this will be same as the proportion, which is 0.4. Unfortunately, that doesn't help us because all of them show 0.4. But the next one can help us when we do P times 1 minus P divided by N, which is 0.4 times 0.6 divided by N is sample size of 50, which gives us 0.069. So of my remaining answers, I'm going to cross these three out. And the question is it skewed right or is it approximately normal? This is where we're bringing in the large counts condition, and we learned about that. Because our population, our proportion that we're working with is 0.4, I can multiply that N times P and N times 1 minus P, and that will tell me if I have enough successes and failures so that we're going to have an approximately normal distribution. So 0.4 times 50 is 20. It's 20. There we go. It's 20. And then this is going to be 30 when I do 1 minus P. And so both, I had enough successes. I'm going to get an approximately normal distribution. The answer is A. All right. And I believe this is our last question that we're going to be looking at. So this one, I do remember this one caused the most difficulty on the test when you guys saw this. So give it a go again. See what you can work through. This one, it's tempting to just do a regular z-score, say x minus the mean divided by standard deviation. And if I do, I've got the sample is 1920 minus 1850 is the true population mean divided by 315. And when we do that, we're going to get a certain value. I actually don't know what that value is, but it's easy to do it that way. And here's where the mistake is. This is what it would be if we were looking at one house from the population and finding the probability of getting that size house or bigger. But we're looking for the probability of getting a sample mean out of 100 in a sample. And the sample mean is 1920. So basically saying, what's the probability of getting 100 homes that are that big out of a random sample? Well, then the probability goes down. And so what we need to first of all find is the standard deviation for a sampling distribution of means, sample means. And that's going to be our 315 divided by the square root of n, which is 100, because there's our sample size again, n. So that's going to be 315 divided by 10, which is 31.5. So in our calculation, we don't want to use 315, we want to use 31.5. So maybe the thing to think about is if you see that there's a sample drawn with a sample size, then immediately you should be going to sampling distributions. If it's asking about a single individual and where they fit in a population distribution, then that's just going to be your regular normal calculations. Does that make sense? All right, so anyways, when we do that, the correct way, we're going to get a z-score of 2.22. And essentially when we do our normal CDF calculation and say, what's the probability of getting, here's my z-score at this point, what's the probability of getting here or greater? This is just a 0.013 probability. All right, you can plug that into your calculator and double check that. Now, hopefully that made sense as we were going through it. If there are any questions on this one or any of the others, certainly feel free to let me know. Are there any questions right now? Okay, I know this is a lot to process. My brain is fried too. I'm just trying to power through so we can see this. All right, so unit 6 and 7, you have an FRQ for each one. We're going to look at 8 to 9. We're just going to get through all 12 units of review, and then it's going to be, well, then we're going to move from there. All right, don't forget you have your homework, your project, that is, which next Wednesday you need to have a problem statement ready. So make sure you're looking at what data you're going to pull from online so that you can run an inference test, and then what question are you trying to answer and what's your hypothesis. If you are running into problems and you're not sure you're approaching it correctly, let me know. I can talk about that with you anytime. But as long as you have that to me by Wednesday, you're good to go. Let me go ahead and call this a day. You can have a wonderful weekend. I will see you next